Now if you know what's going to happen, and you know that we're going to have constructive and destructive interference along the screen, and all you want to figure out is where do you have constructive and where do you have destructive, you don't have to do much. You basically just draw a line here, you see some geometry, and you can figure out pretty fast. We're going to do a little bit more detail, and we're going to tie it to our calculation of general plane wave interference. So we're going to spend a little bit more time than you might see in some optics books, but not too much, don't worry. It's not field theory. So let's recall, let's see, we had the superposition of plane waves. We said interference is just two waves coming together. The diagram looked very much like this. We had two plane waves coming together, and we said, what happens when they interfere? We add them together, we squared it to get the irradiance, we got an interference term. It was a big mess. It looked something like this. If we had the irradiance at point P, we would say, well, it was the irradiance due to one wave plus the irradiance due to the other wave plus this cross term, epsilon naught C, E naught 1 dotted E naught 2, times the cosine of the interference term, which is K1 minus K2 dot R plus, let's see, plus epsilon 1 minus epsilon 2 plus the phases. Right, sorry. All that big mess, right? And that was the interference term. Right? So it looked something like that, where we had the original irradiances of the original plane waves plus this interference term which made it constructive or destructive. Now let's write that more in our current case. Let's see, that was I, let's call it sum, and now we'll say IP. So now if we apply that to what we have here, then we said, well, we're going to give them the same irradiance. They're both going to be I naught, right? So it's going to be I naught plus I naught is 2 I naught. And then if they have the same E field and you square it and you turn this into an irradiance, that's actually 2 I naught again. Because usually to turn this into an irradiance for an E field, there'd be a half right here. But the half is missing in the interference term. So that's plus 2 I naught is that part. And then cosine, and this thing we call delta, is the phase factor. Okay? So we know that when we write it this way, this is just the sum of the interference, or of the two original plane waves, just the sum of their irradiances, and this is the interference term. And we didn't really look at this too closely to see what it does. So now let's make a plot of what's really going to happen as we move around this screen. As we make this plot, well, let's just look at it. We can plot, how do we want to plot it? Like that. We can plot the irradiance at P on this axis. And we can say here is what you would get if you ignored interference. That's 2 I naught. If I have one beam that's 1 watt per meter squared, and another beam that's 1 watt per meter squared, and I overlap them, I should get 2 watts per meter squared. Right? So that's what you would expect. And that's what this predicts if, actually, so at delta equals 0, we'll talk about what delta means in a minute, but at delta equals 0, you actually get, that's 1, you get 4 I naught, you get twice as much. That would seem to not conserve energy, or something bad might happen there. But then if you plot it, you see it's a cosine function, so it's going to go down like this and go like that. Okay? So we know that we can get more than just summing the two when we have constructive interference. Right, that's what's happening there. And that's when the two sine waves are in phase, their amplitudes add. And we know that you can have them out of phase, and you can have it go away. You can have it sum to 0. Destructive interference. And we just have this complicated form because we don't really see the E field. We really observe the square of the E field. That's what kind of made it look this way. So if we just plot it this way, you see actually you do conserve energy. Right? The average irradiance, if one is I1 and one is I2, or if they're both I naught, together they're 2 I naught, the average is here. In some places, in terms of phase, you get more, but in some places you get less. In some places you get twice, some you get 0, and of course the average is just 2 I naught like it should be. But really, the key thing you care about is this axis, is delta. Right? I've plotted this as a function of delta. Right? I plotted basically a cosine delta offset, right? Because this is not 0, so this is the plus 2 I naught. So what is delta? In this case, well, we know delta is the phase factor, but in this case, sort of in the real world, delta is anything, I almost wrote anything that causes a phase difference. And it can be multiple effects. And that's really what we do when we talk about interference. Is we look at different situations where we observe interference and think about what is it that's causing the interference to happen? What is contributing to delta? So Young's double slit is usually the first example, and the thing that contributes to delta is one of them went a little farther than the other. So that's what we're going to calculate next.